Okay, Physics 30 class. In this video, we are going to take on the world's most famous physics equation. E equals mc squared. People see this equation all the time from when they're young. They think, oh, it must be something really special, something amazing, but it's really a simple formula. We're going to look at it. But before we do, we're going to kind of go back to 2 points that we talked about in various other class. The law of conservation. The law of conservation means that we don't lose things, they stay the same. So we have 2 conservation laws. We have the law of conservation of mass, and we did this with chemical reactions, right? When we do a chemical reaction, the weight, the mass of the reactants equals the mass of the products. We don't lose any mass in our system. So the law of conservation of mass states that mass is conserved. The mass at the end of the system is the same as the mass at the start. So we've got the same mass at end That's the law of conservation of mass. We have the same mass at the end as at the start. And we think about this in chemical reactions. That's where we started. Then there's also the conservation of energy. And we talk about this when we talk about thermodynamics and physical science, that energy is neither created nor destroyed. Neither created nor destroyed. It just changes forms. So these used to be 2 completely separate topics from each other. There's the law of conservation of mass, which said that at the start of our chemical reaction, the mass will be the same as at the end. Then there's the law of conservation of energy, that energy is neither created nor destroyed, it just changes forms. And in a chemical reaction, we talk about that energy is stored in chemical bonds and can be released from those chemical bonds or absorbed back into making new chemical bonds. But this guy relates energy and mass. It's a way to convert from energy to mass and back. So what does this formula mean? Well, this E stands for energy, and that's measured in joules. And this M stands for mass. And in this one, we have to watch out that mass is in kilograms. What does C stand for? Well, the speed of light. We do that in meters per second, 3.00 times 10 to the 8 meters per second. And all this says is that energy is equal to mass times the speed of light squared. Energy is equal to the mass of the object times the speed of light squared. What this means is that we can start with some mass, and we can trade some of that mass for energy. Okay, so I can start with 4 kilograms of mass. And I can trade some of that mass to get like 3.5 kilograms of mass, not off, of mass, plus some energy. Likewise, because this is physics, if I can go one way, if I can go from 4 kilograms of mass to 3.5 kilograms of mass plus energy, I should be able to work my way back. Okay, so that's all this formula does. There is 2 variables in it, and this is a constant. So 2 variables. If we know the energy, we can determine the mass. If we know the mass, we can determine the energy. Now let's take a look at a couple of examples to see how this works. Okay. If we were able to convert 6 grams of matter completely into energy, how much energy would we create? Okay, that's our first question. Then how could we do this? All right, so we're going to take 6 grams of matter and turn it completely into energy. So let's take a look. Our formula, E equals mc squared. What do we know? Energy, we don't know. Mass, we do know, 6 grams, but we need kilograms for this. So 0.006 kilograms. C, 3.00 times 10 to the 8 meters per second. I believe that's the correct number. We could always go to our physics sheet and make sure. I'm just going to pull that up on my computer here. My reference materials. 3.00 times 10 to the 8 meters per second. Okay, so I wrote my formula a little too close here, so I'm going to move it over. Energy equals mass times the speed of light squared. Well, I just substitute in what I know. Energy is equal to 0.06 times 3.00 times 10 to the 8 squared. Throw this into Desmos or some other calculator. I'll just run it through Desmos here. Since I find that one works so nicely with the powers. Pulling it up on my old iPad takes a little longer. So 0.006 times brackets 0.00 times 10 to the power of 8. And then I'm going to square that all. I get 5.4 times 10 to the power of 14 joules. Times 10 to the power of 14 joules of energy. Okay. Well, that was pretty easy, actually. The question is, what does this exactly mean? What does it mean to have 5.4 times 10 to the 14 joules? I'm just going to pull up a website here. Energy density from Wikipedia. There's a chart of energy density. Okay, so let's take a look at gasoline. All right, so where is gasoline? Gasoline, gasohol, jet fuel. Oh yeah, we'll just go with gasoline. 43 million joules in a kilogram of gasoline. So if I burn 1 kg of gasoline, I get 43 million joules of energy. So converting the 6 grams completely into energy, well, that's like burning how many? Well, I'm just going to divide this. Nope, can't do that. I'm going to take my answer here. 5.4 times 10 to the power of 14. I'm going to divide it by 43 million. I get 12 million 500, about 12 point, yeah, about 12,600,000 kilograms of gas. This means if I'm able to turn 6 grams of matter completely into energy, it would be the same thing as burning 12,600,000 kilograms of gas. That's a lot of gas. So there's a lot of energy in a very little bit of matter. Now, how can I do this? How can I convert 6 grams of matter completely into energy? Well, it's possible with matter antimatter reaction. You don't need to know much about this, but there's this thing called antimatter, and it's kind of the opposite of matter. It's like there's a electron, which is negatively charged, then there's a positron, which is positively charged. They're kind of the same thing, but one's negative charge, one's positive charge. Just like there would be a proton and an antiproton. Proton is a positive charge, and antiproton would have a negative charge. A lot of the other stuff would be the same. Now, what happens if I have 3 grams of matter and 3 grams of antimatter, and they collide? They will completely annihilate each other, and you will get this much energy from it. So if I could get 3 grams of matter and 3 grams of antimatter together, and I was able to collide them, then I would get this much energy here, which is the same as burning 12 million kilograms of gas. That's like more than 12 million liters of gas. So just 3 grams of matter with 3 grams of antimatter, we're going to get this destructive force. Now, antimatter doesn't really exist in reality anymore. We can make it. It's very expensive to make. It costs, I don't know, there's a video on YouTube about it costs over $1 trillion to make a gram of it. It's very difficult to make, and it's also very difficult to hold, because you have to hold antimatter completely away from regular matter. Because if you ever let regular matter and antimatter collide, well, you are going to be in trouble, because you're going to get a lot of energy. That's going to be a big explosion. All right, so using this formula is pretty simple. There's just 2 variables. We know one of them, we can figure out the other one. Now let's take a look at this next one. A gram of TNT, when exploded, produces this much energy. How much mass is converted into energy? Okay, so we take a gram of TNT, we do the explosion, we get this much energy. And this is a standard amount. 1 gram is that many joules. How much mass is converted into energy? Well, let's see what we've got here. We've got our formula. Energy is equal to mass times the speed of light squared. Now in this one we know the energy. So energy is equal to 4184 joules. Mass is equal to, well, we know there's a gram of TNT, but that's how much we start with. We're asking us how much mass is converted into energy. This is called the mass defect. And we know the speed of light is equal to 3.00 times 10 to the power of 8. Okay, so we've got our formula right here. Let's fill in what we know. 4,184 joules is equal to m times 3.00 times 10 to the power of 8 squared. So we just rearrange this formula to get m is equal to 4,184 divided by 3.00 times 10 to the power of 8 squared. And I can just type that into my calculator. 4,184 divided by, where's my divided by button? 3.00 times 10 to the power of 8. And then I square it. And I get 4.6 times 10 to the power of 14. Negative 14 kilograms. So there's that much mass that has been turned into energy. Now that's not a lot of mass. If we times this by 1,000, that's going to be what? 4.6 times 10 to the negative 11 grams. So it's not even close to a gram. Not even close. And it would be a few protons, because proton is 10 to the minus 27 grams. So that should be like quite a few protons. But this is the mass defect. That's how much mass was turned into energy. Now, this isn't something that we can weigh, really. 4.6 times 10 to the minus 11 grams. We don't really have a lot of weighing tools that would allow us to weigh something that precise. They do exist, but not anything that we can access. So we're going to use some of these facts from before, and we're going to look at this. What is the mass defect of the Tsar Bomba that exploded with the equivalent of 50 megatons of TNT? Okay, the Tsar Bomba was the world's largest nuclear weapon that's ever been exploded, and it exploded with force of 50 megatons of TNT, which is like saying 50 million tons of TNT. Now, this is like saying it exploded with a force of 50 billion kilograms of TNT. So if you took 50 billion kilograms of TNT and exploded it, that's how big this Tsar Bomba was. I'd show you the video. I don't have it on my YouTube on here. Now, we know that 1 gram of TNT is equal to 4,186 joules. I think that's the number, 4,184 joules. Right, 1 gram of TNT is equal to that many joules. So we're going to have to figure out how many joules this is. Well, if it's 50 million tons, that's 50 billion kilograms, that's 50 trillion grams. So now we can figure out how many joules of energy are produced. So we just write up our formula like before. How many joules are there in 50 trillion grams TNT if there is 4184 joules in 1 gram? So I just do 4.4184 times 50 trillion is 5. Let me just do this right. 5 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 10 to the power of 13. I get an answer of 2.092 times 10 to the power of 17. Okay, so the Tsar Bomba, when it exploded, it released that many joules of energy. That's a lot of joules of energy. Let's go back up here. You can see up here, 6 grams release 10 to the 14 joules of energy, and this is 10 to the 17 joules of energy. So it's a lot more than 6 grams. So now we want to find the mass defect. We know the energy, so let's write out our formula. Energy is equal to mass times the speed of light squared. So our energy is 2.092 times 10 to the power of 17. It's equal to mass times the speed of light squared. Now, I don't need to write in what C is every time. We can just leave it as C. So we divide both sides by C squared. I get mass equal to 2.092 times 10 to the power of 17 divided by C squared. Now I just do that on my calculator. I just type that in, 2.092, and then, nope, I need to do this right, times 10 to the power of 17, close the brackets, divided by 3.00 times 10 to the power of 8, in brackets, square that, 2.32 kilograms. So, this Tsar Bomba, when it exploded, it converted 2.32 kilograms were converted into pure energy. So if you weighed the Tsar Bomba before explosion, it might weigh, let's say, 2,000 kilograms. And after explosion, if you could collect all the bits and pieces to it, good luck with that, all the bits and pieces to it would no longer weigh 2,000 kilograms. They would weigh 2.32 kilograms less than 2,000 kilograms, but 1,997.7 kilograms. So before explosion, now I don't know if this is actually the weight. After explosion, all the bits and pieces of it, you have to gather them up from a long ways. This is a big explosion. Right, so before explosion it weighed 2,000 kilograms. It didn't actually weigh 2,000 kilograms. I'm just saying that as an example. Then after explosion it would have weighed 1997.68 kilograms. 2.32 kilograms later. And that 2.32 kilograms actually got converted completely into energy. All right, so that is what E equals mc squared is, and that is what mass defect is. It's a rather simple formula, and it has its place in nuclear energy. So it's used a lot when we're dealing with nuclear energy, like nuclear bombs and nuclear power plants.